They're everywhere, all around us, totally invisible, and you'd think pretty much weightless. But the gases that make up our world, they're actually following a really strict set of rules. Powerful laws that, get this, explain everything from how we breathe to how we power the entire planet. So let's dive in and uncover the secret life of gases. Ever feel under pressure? Yeah, we all know that feeling, right? We use it to talk about stress all the time. But what if I told you that right now, this very second, you are literally under immense physical pressure?
Yeah, that's right. The huge column of air stretching all the way from your head to the edge of space, it's pressing down on you with the same force as a bowling ball balanced on your thumbnail. I'm not kidding. The only reason we don't feel it is because, well, we've evolved to live with it. But make no mistake, that atmospheric pressure is a real, powerful force.
Okay, so this is where things get a little weird and our intuition can totally lead us astray. Let me ask you this. Who do you think exerts more pressure? A 7-ton African elephant or a 120-pound figure skater? It's got to be the elephant, right? Wrong. See, the elephant's massive weight is spread out over its big feet, coming out to about 14 pounds per square inch. But the skater? All of their weight is focused on that tiny, razor-thin blade, and that creates a pressure of around 30 pounds per square inch, more than double the elephant. Wild, right?
And that little example brings us to the big idea here. Pressure isn't just about how much force there is. It's about how concentrated that force is. It's all in that simple formula, P equals F over A. Force divided by area. So you can crank up the pressure by pushing harder, sure. Or, like our figure skater just showed us, you can keep the force the same and just shrink the area it's pushing on. It's all about focus.
All right, so now that we've got a handle on pressure, let's check out some of the simple, honestly elegant rules that tell us how gases are going to behave. And we'll start with a few puzzles you've probably wondered about.
So, you've seen the warning on a can of aerosol spray, right? Do not incinerate. Contents under pressure. But what's really going on there? Why is it so dangerous to heat up a sealed can, even if you think it's empty?
Well, the answer is something called a Munton's law. Think about it. The can is a sealed container, so its volume is fixed. When you add heat, you're giving the gas particles inside a shot of espresso. They start zipping around like crazy, slamming into the walls of the can harder and more often. That, right there, is an increase in pressure. And if you keep heating it, well, eventually the pressure gets so high, the can just can't take it anymore. And boom.
Okay, here's a less explosive puzzle for you. Picture this. You've got a party balloon, perfectly inflated. You take it outside on a really cold day, and a few minutes later, it looks all sad and droopy. It's shrunk. So what gives? Where'd all the air go?
Spoiler alert, the air didn't go anywhere. It's all still in there. What you're seeing is Charles's law. See, when the pressure is constant, like the atmosphere pushing on the balloon, the volume of a gas is tied directly to its temperature. So when the gas inside that balloon gets cold, its little particles slow way down, they huddle together, and they just don't take up as much room. And voila, the balloon shrinks.
All right, now let's talk about something we do, 20 times a minute without even thinking about it. Breathing. It feels totally automatic, right? But it's actually a perfect, real-world demonstration of our next gas law. So how does it actually work? How do our lungs pull air in and push it out?
It all comes down to Boyle's law. When you go to take a breath, your diaphragm muscle pulls down, making your chest cavity bigger. This increases the volume inside your lungs. Now, Boyle's law says that when volume goes up, pressure has to go down. So suddenly, the pressure inside your lungs is lower than the air pressure outside your body. And what does air do? It rushes in to fill that low pressure space. Exhaling is just the opposite. It's such a simple and honestly beautiful system.
So, okay, we've got these different rules, right? One for pressure and temperature, one for volume and temperature, another for pressure and volume. It kind of seems like a bunch of separate ideas. But what if I told you they aren't separate at all? That they're all just different pieces of one single giant, super powerful master key?
Let's put the puzzle together. We've got Boyle's law connecting pressure and volume. We've got Charles's law connecting volume and temperature. A Munton's law connects pressure and temperature. And there's one more piece we haven't mentioned, Avogadro's law, which just says that the more gas you have, the more volume it takes up. Pretty obvious, right? So what happens when you snap all four of those relationships together? You get this. The ideal gas law. PV equals nRT. This is it. This is the master key we were talking about. It takes pressure, volume, the amount of gas, and the temperature, and wraps them all up into one neat, tidy, and incredibly powerful equation. With this one formula, you can figure out almost anything you need to know about how a gas is going to behave. It is, without a doubt, one of the cornerstones of modern chemistry.
Okay, so the ideal gas law is amazing when you're dealing with one type of gas. But what about the real world? What about when you've got a whole crowd of different gases all mixed together? Like the air we're all breathing right now? How do they act in a crowd? And how do they get from place to place?
Well, according to Dalton's law, gases in a mixture are kind of like polite strangers at a party. They basically ignore each other. The total pressure of the air around you is really just the pressure of the nitrogen added to the pressure of the oxygen, added to the pressure of the argon, and all the other trace gases. Each one just does its own thing and contributes its own little bit, its partial pressure, to the grand total.
All right, final puzzle for you. We've all been there, right? You get a shiny helium balloon, it's floating high and proud, and the next morning it's already sinking towards the floor. Meanwhile, a regular old balloon you blew up with your own breath will stay inflated for days. What is going on there? Why does helium escape so fast?
The secret is Graham's law. See, the skin of a balloon isn't a perfect solid wall. It's full of tiny, microscopic holes, and the process of gas sneaking out through those little holes is called effusion. Now, what Graham's law tells us is super simple. Lighter gases are faster. They move quicker and can find and escape through those holes way more easily. Since a single helium atom is way, way lighter than a nitrogen or oxygen molecule, it's like a tiny escape artist. It just zips right out of the balloon much, much faster.
And this really drives the point home. Just look at the difference between super light helium and, say, a real heavyweight gas like argon. The helium particles are so light and fast, they're just pouring out of the container. Meanwhile, the big, slow, heavy argon particles are barely making it out at all. The takeaway couldn't be simpler. Lighter means faster.
So, there you have it, the fundamental rules of the road for gases. But this isn't just about party balloons and spray cans. These exact same laws are absolutely critical in some of the most important, high-stakes areas of science and technology.
I mean, think about scuba diving. For a diver, understanding Boyle's law, that relationship between pressure and volume, is literally a matter of life and death. As you come up from a deep dive, the water pressure around you drops and the air in your lungs expands. If you come up too fast, well, it can be catastrophic. And how about Graham's law? That simple idea that lighter gases move faster? That's the core principle used to enrich uranium for nuclear power plants. It's how they separate the slightly lighter uranium-235 from the heavier stuff.
And that's really the amazing thing about all this. These simple rules govern everything from a sad, deflating balloon all the way to enriching uranium for nuclear energy. It's the same science. Simple, predictable rules are at play everywhere. And it really makes you stop and wonder, what other invisible laws are out there, shaping our world, hiding in plain sight, just waiting for us to figure them out?